Hi everyone, my name is Andrew Schoen, and today I'll be representing my team, which includes my co-authors Curt Henrichs, Mathias Strohkirch, and Bilge Mutlu, in telling you about our paper titled Authr, a task authoring environment for human-robot teams. This project grew out of work done by our lab and by our colleagues that showed that there was a bit of a problem happening in collaborative robotics. While collaborative robots appear to have a lot of potential to improve the quality of work, this promise doesn't seem to have fully panned out in practice. A recent ethnography by Mathias et al. Showed that the capabilities of collaborative robots were frequently poorly utilized. Instead of being utilized for their intended purpose, collaborative human-robot interactions, they were typically deployed for simple non-interactive purposes. The likely culprit of this discrepancy was that programming robots and designing interactions are two different types of skills, and engineers are usually only trained in the former. In other words, engineers are accustomed to thinking of robot programming as a simple series of instructions rather than as an interactive process between two agents. For this reason, we sought to ease this process for engineers as they create robotic programs, providing a scaffold that both allows designers to create collaborative programs while leveraging the experience they do have in single robot programming. We also employ an approach considerate of the types of information these designers have on hand when constructing their programs. We create a novel representation for these types of tasks and an interface which utilizes this representation. We then evaluated this approach with a series of user studies. As I said before, we first wanted to create a representation compatible with the types of task descriptions currently available to engineers in order to minimize the learning curve. These types of task descriptions typically involved booklets or lists of actions to perform. We also wanted this representation to be able to sufficiently define robot behavior. To accomplish both of these goals, we combined the concepts of hierarchical task analysis, Thurbligs, and a novel parameterization approach. Hierarchical task analysis, or HTA, is a way of representing tasks in a structured hierarchical manner. This hierarchy allows users to build up tasks from smaller subtasks. Execution in these hierarchies is performed by executing the trees from left to right. We utilized a simplified version of HTA with limited depth in our representation. This included the top-level plan, its tasks, and the subtasks that make up those tasks. To represent subtasks, we utilized another concept called Thurbligs, which are used to specify human work in understandable ways. There are 18 Thurbligs in total, and these include purely physical actions like grasp and transport load, as well as more cognitive actions such as search or inspect. For the implementation of our current interface, we focused on the purely physical Thurbligs, those being transport empty, grasp, transport load, release, rest, and hold. Finally, since these subtask Thurbligs needed to be robot executable, we needed a way to more fully describe them. To do this, we introduced the high-level parameters of agents, things, and destinations. Agents are the humans and robots in the scene. Things are the objects they can manipulate, and destinations are the semantically meaningful representations of locations in the workspace, such as goals or waypoints. In this way, for example, the transport-loaded Thurblig could be specified by who performs it, the agent, what is being transported, the thing, and where it is being transported to, the destination. A full set of high-level parameters can be seen here. As you can see, all Thurbligs except the agent parameter, which turns out to be a bit of a special case. Unlike the things and destinations parameters, the agent parameter is optional and can be left unspecified. Since providing the agent parameter is akin to allocating the Thurblig to that given agent, if unspecified, this indicates that the best agent will be selected automatically to perform this action given the constraints and goals of the program. Thurbligs also accept low-level parameters such as time and cost estimates for human and robot workers, or the grip amount for a grasp, for example. These low-level parameters are therefore used to fill in any remaining gaps of knowledge that the robot may need for execution, should it be assigned to it. I mentioned time and cost estimates, and these are used to assist in allocating agents. These two values are used in the optimization step, which tries to find the most optimal allocation of agents while minimizing effort and time. Users can adjust the relative strength of these two weights at a high level. Another key part of this representation is the verification that is incorporated. For each of the Thurbligs, we constructed a set of preconditions and postconditions that dictate what requirements of the state must be fulfilled in order for the Thurblig to execute, and the effect that Thurblig has after its completion. For those familiar with planning in the Planning Domain Description Language, or PDDL, these are equivalent to predicates and effects, and like PDDL actions, these conditions can reference the parameters that are given or the state of the world. Thus, for a Thurblig like transport loaded, the thing being transported must be in the agent's hand or gripper, and the destination location must be clear of other things or agents. These preconditions and postconditions are encoded into Z3 and checked during the plan construction to ensure that the programs are error-free, and also used in the allocation process to ensure that the plan remains error-free afterwards. An extremely simple case is where there's a mix of allocated and unallocated Thurbligs. Due to these constraints, the same agent would need to be allocated to all of them because the object being gripped must be gripped by that same agent to proceed to the transport loaded. We use this entire representation to create Authr, a ROS-based authoring and simulation tool with a web-based front end. The design of Authr is meant to be easy to use and approachable for task designers. There are 3 tabs: Setup, Plan, and Simulate. In the Setup tab, designers can create and customize the scene with agents, things, and destinations. They can also configure the relative strength of those effort and time minimization objectives. The entire scene can be modified with both mouse and numerical input. In the Plan tab, a Kanban-like interface is used to represent the plan, tasks, and Thurbligs. In addition to the canvas, which contains this plan structure, there is a left-hand sidebar from which users can select Thurbligs and drag them into the plan. Clicking on this sidebar provides users with information about that Thurblig. Information in detail is shown in the right-hand sidebar and is contextual based on click events. Clicking on a task shows information about that task, for example. Tasks can be renamed and exported from their detail view as macros, which can be dragged into the plan much like Thurbligs. Clicking on the Thurbligs in the task allows users to parameterize them with high-level and low-level parameters, and also view information about any errors the program has detected through verification. In the Simulate tab, the optimized, fully agent-allocated result can be viewed in the timeline, and the entire interaction can be simulated. When simulating, a hand representing the human moves around the space, and the robot executes its actions based on the Move It motion planning software. While each Thurblig executes, it is highlighted in the timeline below. We constructed 2 sets of evaluations of this software with engineering students. The first was informative analysis of an early version of the Authr interface. This version lacked a number of features present in the final version. Specifically, there were no macros and no functioning Simulate tab or automated allocation. Additionally, locations of things and destinations was facilitated through a programming by demonstration inspired process in which users moved the end effector of the robot around the simulated space and recorded positions and orientations. For this evaluation, after being instructed how to use the interface, participants watched a video of a task in which the actor moved a set of 3 different objects into a container and were then asked to recreate that task in the Authr interface. We discovered a number of themes during this evaluation. First, users tended to cluster tasks into groups based on the focused object, despite no requirement or instruction to do so. In fact, they tended to see this parallelism quickly, with a number requesting a way to take advantage of this through duplication or reuse. Second, a number of users expressed confusion about the demonstration-based configuration of the 3D environment. While this type of specification may be highly useful with physical robots in some programming environments, this approach seemed unnatural for users in our virtual environment. Finally, users expressed a desire to view the results of their program as it executed in order to check their work. Based on these emergent themes, we added the ability for users to reuse tasks as macros and switched to direct manipulation of objects for configuring the scene. The inclusion of the simulation view had already been planned, but the feedback here reaffirmed the inclusion of this feature in the final version. The final summative evaluation of the interface involved users constructing 2 plans in Authr. One in which they could utilize the automated agent allocation, and the other where they were asked to do this manually. This evaluation revealed several themes. The first was that users tended to quickly become frustrated or apprehensive in the manual condition after understanding all of the considerations that manual allocation requires. To combat this, many in the manual condition adopted strategies and heuristics to cope with these complexities. For example, one participant decided to average across actions in order to assist in assigning agents. This strategy formation was the second theme we found. The third theme was that, unfortunately, these strategies and heuristics were frequently incorrect or applied inconsistently, resulting in suboptimal results. Some of these errors were more conceptual, in which users failed to consider certain possible benefits of collaboration in allocating certain agents. Others were more technical, in which users failed to appropriately weigh various objectives or inconsistently applied their heuristics. Finally, we found that users in the automated Authr allocation condition exhibited a more streamlined workflow in the interface. In the manual condition, users had a fractured approach in which they had to continuously and sporadically alternate between referencing instructions and data, performing calculations, adding to or changing the program, and parameterization of third-legs. In contrast, users in the automated allocation condition had a much more linear workflow of reference to calculation to configuration and then back. In conclusion, we set out to see how we might assist engineers in the process of designing collaborative robot programs by considering the workflow that would enable this translation, the authoring environment that would be utilized in that workflow, and an evaluation for that workflow and tool. Our findings indicated that the representations we had developed served as an appropriate framework for modeling existing tasks, and our interface and approach allowed for a better facilitation of collaborative task authoring than more manual approaches, creating programs with a more streamlined workflow. I would like to thank my amazing advisor and co-authors, since it was definitely a team effort. I would also like to thank our funding sources for supporting this research and for your interest in time.